Okay, so far we found out a bunch of stuff about, and we got what the amplitude is, the amplitude of the vibrations in terms of the damping ratio and the original F naught and K. But now let's figure out what kind of force is transmitted back to the wall. Remember, we originally had this sort of problem. We had a spring here, and we had a damper, and we have a mass, m, and we were forcing it, F naught sine of omega t. Right? That was our original problem. And that amplitude is part of the solution x. Right? X was equal to, turns out, the solution to this, the complementary solution, is xp is equal to a sine of omega t minus phi, where the amplitude is defined here and the phase is here. We said that that was the particular solution, but it turns out that that's the important part. Okay? We said that the full solution, the general solution, is the complementary solution plus the particular solution. Now, as time goes on and on and on, time approaches infinity, this complementary solution, remember that was the solution for the unforced vibration to the homogeneous form of the equation without the forcing term, right? And what happens with that solution, that complementary solution? It dies out over time if your zeta is, well, in any case, it doesn't really matter. Yeah, it always is going to go away. You're going to have some decaying exponentials involved. So that's the part where if you just displace this initially and have a little bit of initial velocity, well, it's going to do some stuff for a while, but eventually it's going to go to zero. So as time approaches infinity, this complementary solution goes towards zero. The particular solution is all that's left. Okay? And so that's why this particular solution is so important. Finally, yeah, let's get back to the forces on the wall. Well, this was K and this was a C. Well, what's the force on the wall then? Well, we did the free body diagram on the mass before. Well, the force on the wall is going to be K times X and C times X dot towards the right. So let's go ahead and figure out what that is. The force on the wall combined is Kx plus Cx dot. Okay. Well, x dot, I guess I should say this is the particular solution, right? Let's be more careful there. Get rid of this fact here. It turns out that that's all that's important in the long run. Yes, there's some initial transient stuff, but let's only consider the long run there. Then xp dot, let's plug this in. This is going to be a cosine of omega t minus phi. Okay. This becomes K A, oops, this is A omega. This is K A xp, which is, well, okay, no, sorry, K A sine of omega t minus phi plus C A omega, or maybe I'll write A C omega, cosine of omega t minus phi. All right. Now look here. We have something similar. We're going to use our identity again. We've got the sum of a sine and a cosine that fits this form here. So the cosine is the A term. So our amplitude of the force on the wall is F naught. Let's say that thing there. The amplitude of the force on the wall. So force on the wall naught, amplitude, is going to be the square of a squared plus b squared. Well, that's the square of Ka, that was all squared, plus C omega, AC omega, that is all squared, and the square root of that. And that there is, well, let's take out the a square root of K squared plus C omega. That squared. So the force on the wall is that times the cosine, let's see, times the sine, the actual force on the wall, the total force on the wall, is F wall naught times the sine of omega t. Yeah. And in general, we could have some sort of phase here. We might have some additional phase. Well, I guess that, no. It was of that form, right? Yeah, just sine of omega t. Cool. Okay, so that is the force on the wall. It has this amplitude. So it turns out that's just that amplitude there, that amplitude, which is F naught over k times alpha. So the amplitude that's on the wall is F naught over k times, well, we're just going to write k squared plus c omega, that squared, all over the square root of this business here. K minus m omega squared, that squared, plus c omega squared. Okay. And I claim that there's a different way of writing this. I'm going to say that we know that we can write the bottom of this as 1 minus r squared, that squared, plus 2 zeta r, that squared, all of this big square root. Turns out the top can be written as, let's go ahead and say 1 plus 2 zeta r, that squared. So let's figure out what that is. Oh, and then I think we can get rid of the k here. So I claim that that's true. Let's go ahead and see if it is. Let's see if that simplifies to whatever it is there. Okay, so all we really have to do is look at that part. That becomes the square root of 1 plus 2c over 2 root km times r is omega over omega n, that's root k over root m. And this here is all squared. Okay, well, what's that equal to? That's equal to the square root of, well, let's go ahead and just simplify in place. The 2's cancel. The k's, they multiply together. The m's cancel. This becomes a k. All right. It's going to be nice to let's bring out k. Let's multiply by k over k. Okay. And let's go ahead and bring this top k inside. So it becomes 1 over k on the outside. This becomes a k squared plus, that gets rid of that, plus c omega, that all squared. Okay, we were right before. So that is equal to, as we had before, f naught over k times the square root of k squared plus c omega, that squared, all over the square root of the stuff we had. All right. That is the amplitude of the force on the wall. And so this helps you figure out, as a function of your vibrations, the forcing function, F naught, what force does the wall actually see.